take the G, consider it as your choice, which is very much close to your original target function F. So that is how we are how the neural network are existed. And but here the catch is here, it is only if I explicitly write it up this one. um, this one we could f of x minus g of x nor is less than epsilon. I mentioned x explicitly, like for all x belongs to for all x belongs to inside the interval here, in the diagram at least you can see minus 2 to 2. It doesn't matter what happens outside of this one. You don't care, like our target function, it may come outside of the epsilon band. It doesn't care about it when your choice of looking at only your interest sitting inside this one only. So this is how the local density. But even even if you think of this band keep continuous like this, the epsilon band, but your g, the targeted g, uh, the choice of g which you are looking for close to f, which may come outside of that one. So that density, what you are looking G, which is close to F, it is inside a compact set. That is what we discussed last time. That is how the density is here is a relative density. It is not a universal function approximation for everywhere in the entire domain. We don't talk on it. It is we look at a particular region. There only we would train or we would look at the neural function which is close to it. That is how the definition builds. So that for that, like so if you ignore this one, then you are saying that neural networks are approximating the entire function f equal to x square everywhere, but that is not true. The f of x equal to x square only can be possible in a closed and bounded region. So um, to mention this one very clearly, or write it up in a definition format, I could say. Mm, I will write it maybe like this. It is same that we have discussed last time, but I just wanted to mention it in some way of language which we write in the density concept. So usually the dense subset, or okay, let me write it up so that it will come automatically. Uh, let I'm writing in general. It is, you can think of that particular case of set, because x here, it is need not be uh, just the real numbers. Rn or anything, like it can be objects of any kind. That is why I'm just giving it here x, and the metric d, I'm choosing it here, be a metric space. And let's say uh, a t is subset of x. That is what I think I have illustrated this one very much. Okay, I written here y. I'll go with y only. uh, I don't get confused again. So let y is subset of x. A subset s is subset of x is d-dense. D-densing Y. Understand? This means that I just explained. This is your X. There is a Y locally sitting here somewhere. There is a Y locally sitting here. Now you choose a S, something like this. This is your S. So this is sitting inside X. So now we are saying that this S is dense in X, or S is dense in somewhere dense. That's what we are saying. So that's how that's explained already. So I'm just writing in the formal way of uh, definition format. I didn't write last time. That's what, like, in Y. When do we say that? If the set S is subset of X is a D dense, by the D dense in the sense like it's a metric choice, like the choice of metric, whatever you choose, the distance between the two items, that is of the metric choice. So based on that, the dense property varies. If um, if for every epsilon greater than 0, and for every element small y belongs to Y, you just imagine last time diagram, you connecting it, Y belongs to Y, that means the domain which we are looking, Y is the domain, the compact set, that's what we are saying. Y belongs to Y, the pink color water, you can say. Y belongs to Y, they for every Y belongs to Y, there exist there exist there exists a particle S belongs to S with or such that, you can say, for every epsilon I could give, there exists S belongs to S such that, and just completely writing in the these notations instead of such that uh, d of d is the metric, or d distance between uh, Y comma S is less than epsilon, is a local metric, I mean local density with respect to the set Y, what we are looking at. So you relate with the last time illustration so that you would understand. Like if you wanted to write up in a simplest way of writing, not the this is the clear way of writing up the D density, or of local metric. In general, if you remember the real analysis, we say that um, let's say in general, note I will write up. You say that Q is dense in R, you write up. This is there is no relative here. It is Q is sitting everywhere R. There is no reference or such that Y is required. So Q is dense in R. That means we say that if and only the closure of Q is R. That's what we write. This is the CL is the closure set, closure of. Do you remember closure definition? I don't repeat again. If you don't remember, you just revise your real analysis definition. The closure property, closure of Q equal to R. It holds all the interior points as well as the limit points inside it. The closure I mentioned a little bit here, that in the metric choice CLD, choice of CLD, or you can omit it if you the metric choice is obvious in the closure definition, so I don't need to mention. Q is dense in R, but here in this case we don't write like this because there is a Y sitting inside and the dense property, so that we go the same property in different way. A relative density, like in this case, S is uh, dense in S is dense in, where do you say S is dense in X or Y? S is dense in, we are looking the local in Y, not the whole set. If and only if the closure format of definition, you can say that uh, closure of S intersection, closure of S intersection Y equal to what it should become? You're, you're not relating. It's a dense. It is so important definition, and these relations are so crucial to understand how neural networks are working. And just asking you for our response. What comes there?
Why, sir?
Sorry, what?
Why? Why?
Yeah, yeah. Why? Yeah, right. So that's what, like, no matter whatever you choose, like, you are looking for the local set. That is what here the R is replaced by Y, because we are not looking for the entire universe X here. We are looking for the somewhere dense. That is somewhere dense is Y. That is what, if you look at here, that is what I'm saying. Like we are looking in the density in the here, Y role is -2 to 2, not the entire R, right? So that is why we are a local property of Y equal to X square. We are approximating this one for all X belongs to -2 to 2. This is satisfying with this one. So the density in general, I just generalized this way of writing for anything, any set in a pure mathematical language, so that you don't need of any confusions or anything. Like there is no specific task here, like the function or anything. Where look at here, X is a metric space. That's it. There is, I don't give any what kind of X it is. It may be functions, it can be set, it may be anything. Yeah, that's it. Yeah. Now, from this formal writing, from the last things, I think, yeah, I will go up with something. Hmm, what we can discuss, like few. I think um, we have some kind of uh, okay, let me discuss a particular class, a particular class of neural nets. Let's say, um, let me consider sigma. Let me consider sigma n of g, uh, the class of nets. But now I don't want to take my g as something like where take g as the identity function. Let's take g as the identity function. So that means, like, whatever you posit g of x equal to x, meaning that is g of x equal to x. So now, um, Yeah. Mm. Can you tell me what kind of functions are these? What will happen if you take G as the just identity function, the neural network? It is crazy neural network. What kind of tasks it will do uh, from n to 1? Just think a minute. That means like uh, if you take f belongs to sigma n of g, the f of x can be a typical example. Let's say if you have k neurons, yeah, so you have something like um, beta i's uh, g of ai of x, right? Yeah. So now this g is just the identity function. Then what is this f?
Sir, I guess it follow a linear regression like that because sir,
Hmm,
here our activation function G,
hmm.
if we hidden layer, if we pass our affine function, then
Yeah,
output will be again affine because our gx equal to x, and then we multiply some constant beta I.
yeah, yeah.
It
So
will like form beta 1 equal to a1 x like
mm,
that, sir.
yeah,
Not any impact. So I think it will follow some linear regression,
yeah. Like you will get end up with
multiple
something
linear.
like alpha one plus this one, right? Yes.
Yes, sir. Yes, sir.
Yeah, linear combination of linear functions. It is again a linear equation, right? So it is just simply alpha one x plus alpha two, some kind of this one will come now. Some for some alpha one and alpha two. Now the question is about uh, suppose let me choose a kind of like okay. Now the my question is, that like this is a vector space. This is just, there is no non-linearity. These are all like a simply the mm, mm, the affine maps, or this is just a single again an affine map, that is like it is belongs to again some a an. So where we started with the a star belongs to an, but again it comes with an. Now the thing is usually and this one is, if you don't choose the right choice, then the functional class becomes finite dimensional. So in this case sigma n of g is finite dimensional. It is a finite dimensional vector space. Even you can say finite dimensional vector space. It is a finite dimensional vector space. But if G is like sigmoid or ReLU, in that case, it is not a finite dimension. It is an infinite dimensional function space, continuous. Like no, we can say it is a vector space, so that continuity I will write up like so combining both the statements. So uh, it cannot be it cannot be dense. dense in C of k. C of uh, K is a compact set here. I will where we are discussing always. There is a compact set associated always, even whether I say or not. Always there is a on a compact set. I can say F belongs to on a compact set K. Always there is a local set associated. That's what like dense in K. You agree with this one? Because you are just getting just the linear functions f of x's. You don't have any x square, you don't have any x cube, you don't have any sin x. You can't approximate with this those things. It is just a finite dimensional vector space, so it cannot be dense in ck, because by nature ck I can write up like ck um, is ck is an cannot be dense in ck, which is infinite dimension. Infinite dimensional, I can say literally by extending Banach spaces, so that I'm just writing is a infinite dimensional Banach space. You know it, right? I don't repeat this one. What is Banach space? Yeah. Set of all continuous functions or infinite dimensional Banach space. Say, and of course you have to give some norm that's under a write up like under infinity norm. Yeah, now it is fulfilled, the statement. So now with this, now why I'm making this statement, your choice of G is really matters. If you choose a bad choice G, then the activation function, what you usually called in the technically machine learning technically, but in general we say G is a measurable function. But now if you choose the G as identity function, it is not doing any impactful class of functions here. This class is very just a vector space. Vector spaces can't do anything much beyond a certain limit, because they limit to a finite dimensional space. And even if you try to approximate our function f of x equal to, let's say, our target function. If you target this function f of x equal to x square, um, with the class with the G's identity, and a particular set, let's say k equal to -2 to 2, or 0 to 1, you can choose whatever, no more choice, but you can, and a particular set. Now what close you can go, what closeness you can go, like, okay, that means trying to find out a function G such that, let's say, infinity norm, let's keep it as a max norm, that is like maximum of x belongs to 0 comma 1, the compact set, is that modulus of your target function x square minus your G is something you can go ahead with alpha x plus beta, since that is a linear function, that for some alpha and beta only, as you see here, only it is this one, some alpha and beta. So now I need this answer. In what answer you will get it, what means what is the maximum supremum, what is beyond that you can't reach it. That means like you are trying to approximate uh, f equal to x square in the region 0 comma 1, with a some linear function. So you have some linear function, uh, like maybe going this way or this way, whatever the closest linear function you can bring, that is the maximum possible closeness you can achieve under the supnorm. Can you tell me what was the closest linear function you can draw, which is the g which represents that? What alpha and data you can achieve for y equal to x square? To try this one as an exercise for alpha and beta, it is you can do it. This is not a big thing, you know it algebra. Yeah, we are asking approximate a line close to x square under the supnorm. I need this g explicitly, meaning asking what alpha and beta, which gives the closest x square. Okay, you try this and get it going. So the beyond that you can't reach it, no matter whatever you try it. And try analytically this one, and now try the same as an
So
exercise.
alpha equal to 1, beta equal to 0.
Think that means you are passing a line equation from origin, something like this. Alpha equal to 1, that means 45 degrees line equation, right?
Yes,
You
sir.
can bring, no, that is not, you can see a lot of usually, but that you can approximate much closer. Try it. It is just simple algebra, you can try. Now what my question is,
Okay.
like, looking at the density, like how density impacting, like you can't close, you can't get achieve, whatever choice epsilon you choose, you can't go close by. So that is what we are looking. The epsilon choice, whatever you are getting here, that is error. You can't go beyond that point. The answer which you get here, that is the maximum error. You Our definition is the arbitrary close epsilon greater than 0, but you don't go beyond certain point. That is the limit I am asking, the epsilon limit. What is that? Okay, so you try it out. If you know this g, immediately you will get that for the epsilon limit. So now try the same. This is analytically you try it up, that is easy. And write up exercises for you convince yourself that write a Python program uh, to see the same uh, to see the same uh, for uh, any choice of for any choice of uh, for any choice of number of neurons. It doesn't matter. uh, any choice of any number of choice of the k. The k is like, the number of neurons, number of hidden neurons. Yeah. Always you will arrive some epsilon. It may not be yeah, always you cannot come below certain point. If you change the number of neurons, you will increase the number of neurons, and after a certain point you will reach to a bound. You can't make it lower to that bound. Okay. So that is one uh, example or way of looking at how the classes are not dense. And another, okay, let me number them so that this is a I could say, another B point. Now let's take g of x equal to x power m, some polynomial for fixed m. It is not a, let's say, uh, fixed m, let's say greater than or equal to 1, an integer. Okay. Now what we are looking like, the function belongs to in this class summation uh, k equal to 1 to, what I write usually, I equal to, right, I equal to 1 to k neurons, beta j times g of ai of x. It would become now sigma I equal to 1 to k beta, not beta j, beta I. Now g is x raise m, so that it would be ai of x whole raise m. That means ai, if I explicitly write up, w I x plus b I whole raise m. Now the same analysis do here, and now tell me that is this class dense, and this polynomial class is dense. X raise m, m is some fixed one that is not varying uniformly, but not for every choice of m. If you fix for m equal to, let's say, if you fix m equal to 2, and you are doing it everywhere 2 only. And now you have our own way to think. It's a choice. What do you say? Now the question is like, um, is sigma ng. I'm not writing compact set, and there is always a compact set. That's obvious. Dense in um, continuous over a compact set. What's happening? I'm waiting for your response. Like, it is simple thing, but vector space, function space, all this.
So if m is fixed, then it's finite dimensional, no?
Yeah, right. Finite dimensional in which space?
Uh, if finite insert finite dimension insert a vector space, sir.
Vector space of what? Like which vector space? Here, earlier vector space of affine functions. This one.
It is finite dimensional in affine functions.
No, it's not an affine function. No, it is not an affine function. It is not a linear anymore.
Yes, sir, yes. For m equal to 1 only, if m
Yeah,
greater
yeah,
than
yeah. For an large.
in polynomial function something, sir, polynomial space.
Yeah, it is a um, polynomial vector space. So it is finite dimensional. mm, finite dimensional. Finite dimensional space in I can mention like finite dimensional. Okay, I'll write up mathematics. Finite dimensional space, that is this our g sigma ng is in, let's say, the polynomials of degree less than or equal to m. You know this space, right? Polynomial space or vector space. Polynomials, set of all polynomials of degree less than or equal to m is forms a vector space.
Yes, sir.
Yeah. So now, which implies clearly, which implies what? It is not
Mm.
not dense
Yes,
in
sir.
C of given compact set. Okay, now I need a counterexample like earlier, something like this one, f of x equal to x square. This one, yeah. What can we, like? Let's say if you take the m equal to 2, if you take m equal to 2, then what is happening? Uh, you can't approximate cubic polynomial with this. That's what barrier. Like now, if I take m equal to 2 and as m equal to t quadratic polynomial, quadratic activation, you can say, then your what is the best sigma g approximation uh, no, I don't call it as the best sigma. mm, m equal to 2, um, for m equal to 2, uh, let's say our target function f of x equal to x cube, our target function. Let me write up target function. Now, what is my question is target function. Let's say on minus 1 comma 1. Let's choose something minus 1 comma 1. So what we are looking for, something like x cube. How the x cube uh, diagram? Like somewhere it comes from the below and it goes up symmetric, of course. Minus 1 to 1. This one is minus 1 to 1. So now what best approximate by x square, the not x square, like with this sigma ng will give that. In this case, sigma ng here is n equal to 1 itself. So now I am looking for a target function, a g, f minus g, such that it is like x cube minus, it is a function of uh, alpha x square plus beta x plus gamma, this one will come up like quadratic. Like if you expand this one at max, you can expand to that one only, a quadratic. So what quadratic equation which approximates x cube such that which is closer to it? So what is the epsilon? I'm looking for this one, the epsilon, the maximum possible error we can achieve from this GN, from this um, class of neural nets. What neural net will give this one? So what is this bounding error? You try that one as well. You can check with that. What alpha, beta, gamma, or you don't need of alpha, beta, gamma explicitly to mention it. You can try the algebra to achieve that function on. Like we are always looking for yeah.
So we can do like that x cube minus alpha x square plus beta x plus gamma equal to 0. First assume that where this equation cuts, from that we can find the x value. Then
Okay.
we
Mm.
can we can calculate based on that what's alpha beta gamma satisfied.
Mm. Yeah,
Then from that
you try one. You try one. I'm not restricting you to the ways of finding it out. Find out what best approximation you can achieve. Yeah, that's bounding error. Yeah. So of course it is on a particular interval. You can't try everywhere. Like we have to restrict. Otherwise, it is always be goes infinity. Mm. So minus one to one. That is our choice. The compact set. What we are looking. Okay. So now every time you like try with the Python program to see your uh, the bound error bound. Yeah. So these kind of experiments will give you a clear intuition of how neural networks are and the basic properties are existing. If theoretically if they don't do, practically you can't expect it. Whatever precise data you have, no matter, you can't achieve a neural net which approximates a function. So first of all, theory should satisfy, of course. The theory says very strongly, but practical things like the data problems or computational issues or the way we are approximating the algorithms what we choose, all those things again, they have their own internal bottlenecks where we cannot go as much precision as we want. But theoretically it is always we can talk without having any problem. So if theory fails, no matter whatever neural network, in this case, whatever best algorithms you try, whatever optimization techniques you apply, you can't reach beyond this epsilon. No matter whatever supercomputer you use, no matter whatever best what we call back propagation techniques you use, you can't go ahead with this. This is by limitation. So so that is what, like, you have to check when you are building a new model or something. Yeah, how whether it is a theoretically convergence is possible or not. If theoretically convergence is not possible, then there is no way. So this you have to limit yourself. The neural net classes are theoretically sound. So otherwise you will end up with the error bounds. Yeah.
could we do one thing? So like first we fix our epsilon, so starting like epsilon equal to 10 power minus 4 at minus 5, something like that. After that, we will pass the alpha value as
Mm-hmm.
a small values as a set and beta value as a array and gamma value as a array. After that, we using Python program for each value check which satisfy
No,
that
no.
closeness in the pop.
In Python program, you don't try this one directly like this. You choose from the neural net of by taking g of x equal to x cube, yeah, x square. G of x equal to x square. You try take it, and you try to approximate f of x equal to x cube. You use the neural net function, like use neural net class. Maybe you write on your own, or maybe you can choose from the PyTorch, or maybe
Okay,
what is another TensorFlow or something. Whatever you use it, you use from the libraries, and you restrict the g of x equal to x square. I am not sure that PyTorch or TensorFlow are allowing to use the user defined g of x equal to x
ac-
squares. But if they are not allowing user defined access functions, I am sure that pretty sure they are allowed some way with some flags or something. But if it is not, then you can use your own neural network. That's always better. And check for the approximation is not possible. Okay. Yeah.
okay, sir. Okay, sir.
Yeah. Okay, we'll continue. I think I am giving exercises. So far, I gave last time these exercises 1, 2, 3, 4, and today I gave another two more exercises. Let me name them as 5 and 6. Uh, so I ask you, all of you, implement or whatever the exercise I gave here. Um, I take it as a assignment, and you maybe submit by end of this week, or maybe I can keep it a deadline 7 due, so that you will work on them at least 7, 9, 25.
Okay, sir. We have to submit in
Yeah.
.ipynb file.
No, you just send me email by whatever you write up in a PDF, or you programs, the diagrams. It's everything. There is I don't give any boundaries. You explore
Okay, sir.
on the items what I throwed at you. Okay, there is no limits of it, but at least it is going in the direction of looking at the addressing the problem. That's what I'm doing. Okay. Okay, we'll meet tomorrow. Again, we'll continue a few interesting things.
Oh, okay, sir. Thank you, sir.
Yeah, bye.